Everybody, it's Mrs. Harbin, and we're going to talk about equilibrium. Okay, some of you are thinking, well, she talked about equilibrium when she's talking about delta G. So let's see what we got here. Make sure you read these sections in chapter 17 to go along with this video notes. Okay, so what makes a reaction go? Well, we already talked about increased entropy, decreased enthalpy. We'll get a negative delta G. Okay, so that is a spontaneous reaction. That's spontaneous. Well, there's a case for not spontaneous as well. And then there's the other case. So what makes a reaction go? Three possible results for delta G. Okay, you can get delta G negative. That means the reactants turning into products is going to be spontaneous. Okay, you could get delta G positive, which means the reverse of that would be spontaneous, or this is not, or so reactants won't turn into products, or products will turn into reactants. So what does it mean to be delta G equals 0? That's what's going to be called equilibrium. Okay, and so that means that the reactants can turn into products and the products can turn into reactants. And so we have this double-headed arrow type situation, because maybe the forward reaction is decreasing in heat, so that's favored, but the reverse reaction is increasing in entropy, so the reverse reaction is favored. So what happens is there's a case where delta G can be 0, where the heat and the entropy are working in equal but opposite directions to get equilibrium. So both reactions can happen at the same time. Okay, so equilibrium. What's happening during equilibrium is that the rate of the forward reaction and the rate of the backward reaction are equal. Okay, what's equal at equilibrium? Rate. So here's my bridge analogy of that. All right, so you got people over here and you got people over here. And then the number of cars going this way and the number of cars going that way, every time a car comes off the bridge over here, a car comes off the bridge over here, and so the rate of the cars going from one side to the other is equal, and that's equilibrium. That doesn't mean you have the same number of cars here and here. It just that means that every time a car comes off over here, another car comes off over here. So the forward reaction's going, the reverse reaction's going at the same time. They're both still changing, and that looks like the number of cars over here and the number of cars over there doesn't change, but that's just because they're changing at the same rate. Some people would say, I put a lot of sugar in my iced tea, but it looks like the amount of sugar doesn't change. So we'd say, oh, that's a saturated solution, can't take any more. But what happens is that this every time one sugar molecule dissolves, another sugar molecule solidifies, and so the rate of change of that is equal. So it looks like nothing's happening, but we know that the rate of change is equal. That's what equilibrium is. The rate of change is equal. So it doesn't mean it's stopped, though. It is dynamic. Dynamic means changing. Dynamic means changing. Dynamic, changing, always changing. So equilibrium is dynamic and never actually stops. Okay, so if I was filling this bucket and there was a little hole in there, well, first I'd be putting water in, and it looks like, and water would be coming out, but the amount of water in the bucket would be still filling up. But then we get to a point where it looks like no water's going in or out, but we know water's still going in, water's still coming out. So it's still changing dynamically. These water molecules are different than those ones, and so the water molecules in the bucket are constantly changing, but it looks like the amount's staying the same. What happens if you have a bigger hole, bigger stream of water? You get to a point where it's at equilibrium, and the amount of water doesn't look like it's changing, but we know some's coming out, some's going in, so they're always different water particles. Okay, dynamic means changing. Equilibrium looks equal. What looks equal? I shouldn't say equal. It looks like it's not changing. This stays the same, the amount, but we know they're different water molecules because some are leaving. So dynamic means change. At equilibrium, there is constant change, but the rate at which it's changing stays the same. Okay, so we can write equilibrium expressions because the amounts, the concentrations of reactants and products in an equilibrium system are constant. So a ratio of products to reactants exists. So we have this quantity called Kc, the equilibrium constant. Okay, equilibrium constant. We're going to call it K, and then we're going to say the C is for concentration. So what the brackets mean concentration. Okay, so don't forget that. What do the brackets mean? Brackets mean the concentration. Concentration right now for us, we're using molarity. Okay, so if you take the concentration of the products, if you have one product and another product, and you raise it to the power of the coefficient, you'll be able to compare that to the concentration of the reactants raised to the power of their coefficient. Okay, and if you plug in those values at an equilibrium system, then you'll get a constant number. K is an equilibrium constant. So equilibrium constant, right, it's going to be our K. Okay, and then we can write KEQ for the equilibrium constant. R is for reactants, P is for products. That means concentration, and the COEFF is the coefficient. So we can write an expression for an equilibrium in a chemical reaction. Look, a generic chemical reaction. What's so generic about it? Well, there's no real chemicals. But notice the capital letters are the identity of the substance. The lowercase letters are the coefficients. So why is the C and the D here? Because it's products over reactants in an equilibrium constant. It's products over reactants. That's how we're going to compare them. And don't forget to raise each product to its coefficient power and each reactant to its coefficient power. And then you would plug in the value of the concentration, the molarity. So the Kc expressions don't include values for pure solids. State of matter is important. Okay. Put them in. Put in aqueous and gas. Don't put in liquids or solids. Okay. So do not put in liquids or solids into a KEQ expression. And here's the reason why. If I have a solid, okay, and I measure its concentration in moles per liter, okay, if some of the solid dissolves or reacts, and I look at the rest of the solid, and I measure its concentration in moles per liter, well, the number of moles changed and the number of liters changed, but the ratio stays the same. So the ratio of concentration and the constant doesn't change. We could also talk about water. Water's density is 1.00 gram per milliliter. Okay, so if I have some pure water in a reaction, it's got a density of 1.00 gram per milliliter. If some of the water turns into something else, the rest of the water still has a density of 1.00 gram per milliliter, which is essentially its concentration, so it doesn't change. So when you're writing the KEQ expression, put in products over reactants, concentrations, raised to the coefficients, okay? But don't include pure liquids or solids. Aqueous and gas are allowed, okay? And they need to be in there. Okay, why are solids and liquids constant concentration? Well, here's an example. Okay, so here's a solid. If all of these go away, then I still have these, the concentration of that doesn't change. Okay, still packed together pretty tight. We still have the same number of moles per liter. Same with the liquid. Some of those turn into gas or aqueous or whatever happens to them. You still have the concentration of moles per liter. Here doesn't change. Okay, so the concentration of solids and liquids does not belong in the equilibrium expression. No solid, no liquid, because their concentration is constant. Okay, we're going to write some K expressions. So here's number one, KQ expression. We need to take the products. Oh, look, sorry, you can't go. So we say zinc ion concentration. Say products over the concentration of tin ions. All right, any coefficients? Nope. Okay, so we can't, that's not allowed. Number two, all right, so here we go. We got chloride ion concentration times NH3 because that's a gas. Oh, hey, must have got an email. Divided by the concentration of hydroxide ions and multiplied by the concentration of sodium ions, and that's not allowed. And finally, number 3. Oh, look, there's some iodine, but we're not putting it in because it's solid. We have iron ion concentration. Okay, here we haven't practiced this yet. There's a coefficient of 2, so we need 2 there. And this is the constant expression. So we have the iodide concentration. It's also squared because the coefficient of 2. And the iron 3 ion concentration squared. Okay, that's how you write a KEQ expression. And then what we would do is figure out the number for KEQ by plugging in those concentrations. Okay, not all reactions are at equilibrium. If a reaction can get to equilibrium, it's going to go there now because it's a spontaneous process. Okay, so equilibrium is happens, okay, because one's pushing one way, one's pushing the other way, so you get some of this and some of this. And the reaction will keep going until it's there. And then the reaction still keeps going, but the amounts don't change because the rate's not changing. It's a constant rate. Now, we can always, at any time in a reaction, we can figure out the ratio of products over reactants. That's going to be what we call Q. Because if we don't know it's at equilibrium, we can always do a ratio of how much product there is to how much reactant. The formula for Q is the same as the formula for KEQ, except that we don't know if Q is at equilibrium or not. So we'll have to check it. Let's practice after we figure out what Q means. If you put in the ratio of products over reactants and you don't know if it's at equilibrium, and you get the K, you get the equilibrium constant. Wahoo, you're at equilibrium. Yay. Okay. If you put in a ratio of products over reactants and you get a number that's greater than the equilibrium concentration, then that means that the Q that's not at equilibrium yet, and in order for it to get to equilibrium, you're going to need more reactants. So it's going to have to shift to the left. Okay. If you find out the products over reactants and you find out that it is less than the concentration of the equilibrium constant, the less than the value of the equilibrium constant, that means that this number needs to get bigger. So we're going to need to shift towards products to get bigger. So if Q is not equal to the equilibrium constant, then it's not at equilibrium. The reaction's on its way to equilibrium, and it has to get there by either it's still going to make more products, if it's this case, or it's going to still make more reactants. So let's practice one. Oh, look, it's an equilibrium constant. So they're just telling us that the equilibrium constant is 710. Okay, look, no units. That's okay. We know at the moment in time we're looking at the reaction that these are the concentrations of the things in the reaction. So question 1, is it at equilibrium? Well, let's see. We'll take the concentration of the products over the concentration of the reactants, all gases, so we're good here. And we'll figure out where we're at right now. So plug in the values of 0.58 squared over 0.81 times 0.44. And what we find out is that right now we're at 0.94. 0.94. What does that mean? 0.94 is not equal to 710. 0.94 is Q. That's where we're at right now. 710 is K. That's where we have to go. So Q is less than 710. Well, so now we know that this reaction is going to keep going until it gets to equilibrium, and even then it's going. But that means that this 0.94 has to get a lot bigger. Okay, in order to get a lot bigger, this number has to go up. So which way does the reaction have to shift? It's going to shift towards product. Okay, this reaction will continue towards product. We'll continue to make product. And reactant, but it will get more product to get to equilibrium. Okay. All right, so here's what we need to review. EQ is abbreviation for equilibrium. Equilibrium is dynamic. That means it's changing all the time. But what's the same at equilibrium is that the rate of the forward and rate of reverse is equal. Not the amounts, the rate. K is a constant. You can only change your constant with temperature. It's the products over reactants raised to coefficients. Solids and liquids are not allowed in KQ because their concentration doesn't change. Q is products over reactant at some point in time. We want to know if it is equilibrium or not. Okay. Hey, what can you do in your book to figure this out? Well, Popeyed Cow says read the book. All right. He's doing it, so should you. Look at him. This is chapter 17. Yeah. Okay. Thanks for playing, and we'll work on it in class. Have a great weekend. I think it's still recording. Huh? I think you're seeing all this. So anyway.